The universe stretches outward in every direction, a wide expanse of matter and light arranged across distances so large that they can only be described by comparing them to the speed of light and the time it takes that light to travel. In this vastness, the distribution of galaxies is not random. Instead, it follows a pattern of threads and gaps, where long filaments contain clusters of matter, while enormous voids separate them. This arrangement, known as the cosmic web, forms the largest pattern, detectable across the observable universe. It begins with a background of faint microwave radiation that fills all of space, a remnant of an early era when the universe was young and dense. Over billions of years, gravity draws matter towards slight irregularities in that background, pulling it into long strands while leaving other regions nearly empty. These strands grow thicker as galaxies merge, clusters form, and superclusters settle into position. The result is a network of structure that spans distances measured in billions of light years, connecting objects separated by timescales older than most stars that shine today. From a distant vantage, the cosmic web resembles a system of links and intersections, each segment defined by the gravity of dark matter. Although dark matter cannot be seen directly, its influence is clear from the way galaxies move. Their speeds, orientations, and positions all align with invisible halos that pull them into extended shapes. The largest of these shapes appear as long, luminous corridors stretching across deep space. Observations show that galaxies tend to lie within these narrow regions, creating the appearance of walls or sheets. These walls are not solid, but they are structured, forming boundaries between voids where matter is thin. The contrast between a dense filament and an empty void is sharp, even though both contain vast distances of almost nothing. The study of these patterns begins with light that has travelled for billions of years. When astronomers observe a distant cluster, they see it as it was long before the solar system formed. The distribution of these clusters traces the architecture of the cosmic web. The outermost regions of this structure extend to the limits of detectable light, where galaxies grow faint and their signals blur into background noise. Even in this faintness, the shape of the web continues suggesting that the pattern is universal. The scale is immense, but the principles that shape it are simple. Gravity pulls, gas cools, and stars form within the densest regions. Over time, these regions grow into galaxies, and the galaxies link into larger structures. A scientifically accepted fact sets the framework for this section. The cosmic web arises from primordial fluctuations in the density of matter after the universe cooled enough for atoms to form. Small differences in density become amplified over billions of years, creating regions where gravity collects matter into filaments while leaving other regions empty. This process is supported by simulations that match the observed distribution of galaxies with remarkable accuracy. The match suggests that dark matter plays the primary role in shaping these large-scale structures. Without its gravitational pull, the filaments could not form so quickly or so coherently. A quiet detail often overlooked lies in the arrangement of galaxies within the filaments. Observations reveal that galaxies tend to align their spins with the direction of the filament, or with its perpendicular, depending on their mass. Smaller galaxies often have spins aligned with the filament, while larger ones tend to rotate around axes that lie across it. This alignment is not absolute, but it is measurable and provides insight into the flow of matter during formation. It reflects the influence of surrounding gravitational fields, showing how the shape of the universe on the largest scales affects the rotation of galaxies deep within. A mystery remains in the distribution of voids. These enormous empty regions span hundreds of millions of light years, yet their existence depends on the same initial conditions that create the filaments. Some voids contain a few isolated galaxies floating like islands in a shallow sea. Their evolution differs from galaxies in denser regions. They grow slowly, form fewer stars, and experience fewer interactions with neighbours. Why some voids are larger than others, and why their boundaries take certain shapes, remains uncertain. Models suggest several possibilities, but data remain incomplete. The scale of these regions makes measurement difficult, and each survey takes years to assemble. Three soft ironies drift through this outermost layer of the universe. The first is that the largest structures arise from the smallest fluctuations, tiny variations in density, that existed when the universe was young. The second is that the emptiest regions reveal the most about the whole because the shape of a void outlines the distribution of matter more clearly than the matter itself. The third is that stillness, not motion, defines the early stages of these patterns. The universe becomes structured not through rapid events, but through slow settling, a process shaped by billions of years of quiet gravitational pull. From this vast outer region, the path of exploration will move inward, first through the large-scale patterns of filaments, then into the clusters embedded within them, and eventually into the galaxies that form the building blocks of these cosmic walls. Each step will take the narrative from the broadest structural level towards smaller and more detailed layers, always remaining within the region before advancing. For now, the frame remains wide, stretching across the observable universe, holding the arrangement of matter as a map of everything that can be seen. In this map, the Great Wall appears as one of many filaments, though its size sets it apart. Its boundaries exist within this cosmic web, shaped by the same forces that govern all large-scale structure. Before reaching its outline, the broader network must be understood because every filament draws meaning from the pattern in which it is embedded. The cosmic web continues to expand as the universe stretches. Galaxies drift farther apart, yet their positions within the filaments remain largely fixed relative to one another, because gravity within the filament overcomes the outward expansion at smaller scales. This balance between cosmic expansion and local gravity defines the structure's persistence. Each filament endures because the matter within it is bound. Each void grows because expansion outpaces the weak pull in its empty interior. These interactions create a static appearance in images, yet the motion behind them is slow and steady. Over billions of years, the positions shift, but the pattern remains. The outermost region of the topic rests here at the scale where the largest structures take form. It is a quiet region defined by distance and faintness, yet it contains the imprint of everything that shapes the universe. From this boundary, the narrative will move inward, following the pattern of structure into the specific supercluster known as the Sloan Great Wall, and then deeper into its components. The journey begins with wide space, where the cosmic web sets the shape of all that follows. The observable universe extends across distances that light can only cross over billions of years, and within this space patterns emerge that reveal how matter organizes itself on the larger scales. Surveys that map these distant regions rely on the faint glow of galaxies, each one sending photons that travel through expanding space until they reach a detector. These photons carry information not only about the galaxy that emitted them, but also about the structure through which they have passed. In the present moment, astronomers piece together these signals to trace patterns far beyond the reach of any instrument acting alone. The result is a map of matter as it spreads in sweeping arcs, long filaments and immense voids, each part shaped by gravity acting over billions of years. The focus now narrows from the entire cosmic web to the specific methods and observations that reveal these largest patterns. Light from distant galaxies stretches as it travels a process known as redshift, caused by the expansion of space itself. This redshift allows astronomers to estimate distances on scales that cannot be measured by direct means. By gathering redshifts from millions of galaxies, a three-dimensional map emerges showing not only the positions of these galaxies, but also the structures that connect them. A scientifically accepted fact anchors this section: the Sloan Digital Sky Survey, along with other large-scale surveys, has revealed a universe where galaxies cluster into enormous sheets and filaments. These surveys use wide-field observations to scan broad regions of the sky, collecting data that reveal how galaxies form patterns at scales far larger than any single cluster. One poetic detail appears in the faintness of the most distant objects. Some galaxies in these surveys emit light that has travelled for more than 10 billion years, meaning they're seen as they were when the universe was young. Their signals are stretched and softened by distance, appearing not as sharp points, but as small smudges of ancient light. These faint signals contribute to the broader map, helping define the edges of filaments and the outlines of voids. The farthest regions contribute little individually, yet collectively they reveal the curvature of the larger structures. A quiet scientific mystery lies in the distribution of galaxies across these maps. While simulations predict the general form of the cosmic web, certain features such as unusually long filaments or large, nearly empty voids raise questions about the early conditions that produced them. Some structures appear larger or more coherent than expected from standard models. Whether these differences arise from initial fluctuations, observational bias, or unknown factors remains uncertain. The data continue to improve, yet the larger structures test the limits of understanding. Soft ironies appear when tracing these patterns. The first is that the deepest insights into the larger structures come from the faintest galaxies, whose signals barely rise above background noise. The second is that mapping the universe requires measuring immense distances using light that has been stretched into gentler wavelengths, making the oldest objects look younger in colour even as they reveal older epochs. The third irony lies in the apparent permanence of these structures. They seem fixed, yet they exist in a universe that continues to expand, pulling galaxies apart even as gravity binds them within filaments. The process of mapping the universe involves moving from broad surveys to detailed reconstructions. Each survey builds on the previous one, adding finer detail and expanding coverage. As more galaxies are measured, the map becomes clearer, revealing intricate patterns that resemble interconnected cells. At this stage, the narrative remains in the outer region of the topic, describing the methods and observations that make large-scale mapping possible. The inner structures, including the Great Wall, will emerge as the path narrows further inward. Galaxies in these surveys form clusters that appear as bright knots where several filaments intersect. These knots, known as nodes, often serve as anchors for larger structures. Around them, chains of galaxies stretch outward, tracing filaments that can extend for hundreds of millions of light-years. Though the galaxies move within these structures, their overall positions remain roughly consistent on cosmic timescales. Gravity maintains coherence within these patterns, even as the universe expands. The shapes that astronomers observe today resemble the early distribution of matter in the universe, expanded and refined over billions of years. Another accepted fact underscores this stability. The cosmic web is not static, but evolves slowly. Filaments thicken as matter flows toward them, and voids expand as they drain into surrounding structures. The expansion of the universe stretches space, yet gravity resists on smaller scales, creating a balance that allows the patterns to persist. Observing this balance provides insights into dark energy, the force driving the expansion, though its nature remains uncertain. Even with large-scale surveys, the underlying cause of cosmic acceleration remains one of the universe's quiet mysteries. The faintest galaxies in a survey sometimes fall near the boundaries of detection, their shapes distorted by distance. Yet these boundary cases are essential. They outline the edges of the structures that lie far from the central regions of the map. Without them, the filaments would appear shorter, the voids smaller, and the overall pattern less connected. The delicate balance of faint and bright galaxies forms a tapestry that reveals the distribution of matter across regions so large that no image can fully capture them. Within these vast patterns, the Great Wall stands out as a particularly large filament. Its structure stretches across hundreds of millions of light-years, forming a boundary between several voids. Yet at this stage, the narrative remains outside its specific contours. The focus stays on the broader methods that reveal all large structures at once, showing how astronomers identify patterns that span observable cosmic distances. The Great Wall emerges from this context, but the path remains in the outer region a little longer. Three more gentle ironies align with this mapping process. Only took billions of years for matter to arrange itself into patterns that humans can recognize, with instruments built in decades. Only took trillions of stars to form structures that appear as faint lines when plotted on a screen. only took the entire expansion history of the universe to produce a map that becomes clearer as distance increases. These reflections sit quietly within the narrative, offering perspective without altering the even contemplative tone. The second section concludes with the understanding that mapping the universe reveals more than individual galaxies. It reveals the structure of everything that surrounds them. The next step will move toward the specific region where the Sloan Great Wall lies, narrowing the focus from the entire observable web to one of its most striking features. The movement remains slow and steady, honouring the scale of the structures described. Light moves across the universe at a steady pace, carrying with it the memory of distant worlds, ancient clusters and formations that no longer exist in the state they once held. In the present moment, these photons arrive from deep space, having travelled for billions of years through the expanding fabric of the cosmos. Their journey reveals not only the objects that emitted them, but also the structures that lie between. This section remains in the outer observational region, focusing on how light itself traces the universe's largest patterns, and how the Great Wall becomes visible through the slow collection of these distant signals. The scientifically accepted framework begins with the fact that the farther a galaxy lies from the observer, the longer its light has travelled. Over these distances, the expansion of space stretches the wavelength of that light, shifting it toward redder colours. This redshift allows astronomers to determine how distant an object is, and when combined with large-scale surveys, to reconstruct three-dimensional maps of the universe. Light crossing ancient distances becomes a tool for sculpting the shape of the cosmic web, revealing its filaments, voids and intersections. Each galaxy provides a point on the map. Each cluster adds definition. Each faint smudge deepens the silhouette of the larger structures. A poetic detail appears in the way some galaxies send only a few photons per square metre to Earth across the entire span of their journey. These photons arrive sparsely, sometimes only a handful over minutes, yet they carry the imprint of the galaxy's spectrum and distance. Despite their faintness, they contribute to the vast surveys that outline the larger structures. The universe's largest formations emerge from signals so delicate they seem almost accidental. The structures are immense, yet their discovery depends on particles of light smaller than dust. A quiet scientific mystery lies in how precisely the light travels through an ever-changing universe. As photons cross billions of light-years, they pass through regions of varying density, drifting near filaments, crossing voids, and gliding past clusters whose gravity bends their paths. This bending, known as gravitational lensing, slightly distorts the positions of galaxies. While lensing is well understood, the cumulative effect of these distortions across tens of billions of light-years remains an open question. How much the light's path shifts, how subtly the map is warped, and how those distortions accumulate are matters of ongoing study. Even the clearest images of distant structures contain small uncertainties shaped by these invisible influences. Three soft ironies follow naturally from these observations. The first is that the universe's largest structures depend on the smallest and faintest signals for their discovery. The second is that light, which typically moves in straight lines, reveals curves and bends in space-time caused by gravity's quiet influence. The third is that the farther one looks, the younger the universe becomes, turning astronomy into a contemplation of the past rather than the present. As surveys extend deeper into space, their resolution improves. Instruments measure the redshifts of millions of galaxies, each one mapped to a precise position. From these positions, patterns emerge: long filaments, broad sheets and boundaries where galaxies thin out into voids. Some structures appear surprisingly large, stretching across regions of space that seem too vast for early density fluctuations to have produced. The Sloan Great Wall is one such feature, spanning hundreds of millions of light-years. Yet at this stage of the narrative, the wall remains contextual, a part of the broader network, whose overall outline is just beginning to sharpen in the mapping process. A scientifically supported detail centers on the fact that galaxies do not distribute evenly across the cosmic web. Instead, they cluster into nodes, align along filaments, and thin out near the edges of voids. This non-uniform distribution is predicted by cosmological models where dark matter serves as the scaffolding upon which normal matter accumulates. Light from galaxies along these filaments reveals the densest regions of the universe, while the spaces between them dominated by voids show almost no light at all. The interplay of brightness and emptiness draws the pattern across vast distances. In these maps, the longest and brightest filaments resemble walls thin in thickness yet enormous in length. The Great Wall appears as one of the most extended of these features, but before narrowing inward, this section remains focused on how light crossing ancient distances allows such features to be seen in the first place. The surveys that compile these maps rely on repeated exposures overlapping fields and careful calibration to ensure accuracy. Each observation adds reliability to the final structure, yet no single image captures the full shape. Only through the slow accumulation of light can such an immense pattern be revealed. A subtle detail enriches this understanding. Photons travelling across these distances stretch into wavelengths that no longer fall within visible light. Instruments must capture infrared, ultraviolet, and even radio wavelengths to assemble the complete map. Some galaxies are so distant that their starlight arrives entirely in the infrared, shifted far beyond human vision. These hidden signals contribute to the structure of the web, even though they are invisible without specialized detectors. Photons that began as ultraviolet or bright blue light arrive as faint red or infrared signatures carrying the story of ancient stellar populations and early formations. Another quiet mystery lies in the faintest regions between filaments. Some areas contain isolated galaxies that do not belong to any cluster or structure. Their origins remain uncertain. Whether they formed in near isolation or drifted from neighbouring filaments is still debated. Their presence challenges models that describe galaxy formation as primarily occurring within dense regions. These lonely galaxies serve as reminders that even the largest patterns contain complexities not fully understood. Within this vast field of light, three more soft observations emerge. Only took billions of years for photons to cross the universe, yet their arrival is over in an instant. Only took trillions of stars to form the filaments, yet the light from many of them is no longer detectable. Only took the expansion of space to stretch their wavelengths, yet those stretches reveal the entire cosmic history. As the narrative moves from outer to inner regions, the understanding that the universe's largest structures are drawn from faint ancient light becomes essential. The next section will narrow toward the outline of the Sloan Great Wall itself, beginning to examine its shape within the cosmic web. But for now, the focus remains on the light that makes any measurement possible, the faint signals that reveal the universe's structure at its widest scale. The outline of the Sloan Great Wall first emerges when the accumulated light from millions of galaxies is arranged into a map revealing a structure so vast that it spans a significant portion of the sky in 3 dimensions. Its presence is not obvious in any single image. Instead, it appears when redshifts, positions, and distances are woven together into a continuous representation of matter across hundreds of millions of light years. In the present moment, astronomers view this wall not as a physical barrier, but as a filament, a long, dense stretch of galaxies and clusters aligned into a coherent band within the cosmic web. The transition into this region marks a movement from the broadest scale of observation into a more defined and structured segment of the universe. A scientifically accepted fact provides the foundation for understanding this formation. The Sloan Great Wall is one of the largest known structures in the observable universe, extending across roughly 1 billion light-years when measured along its longest axis. It is composed of several galaxy clusters connected by thinner bridges of galaxies and gas. These components form a continuous chain dense enough to stand out against the surrounding voids. Although it appears as a single unit in maps, its internal structure reveals separate clusters loosely linked by gravity and the underlying distribution of dark matter. These clusters do not merge, but they remain bound within the same filament, tracing a path that stretches across deep space. One poetic detail sits quietly within this enormity. The galaxies within the Great Wall shine with the accumulated light of stars that formed earlier than the wall itself was recognized as a structure. Their starlight emitted billions of years ago now outlines a filament that only becomes visible when viewed from the vantage point of a modern cosmic survey. Each galaxy acts like a lantern suspended across an immense distance, marking the position of structures that cannot be seen directly. The wall's true shape is not an object but an arrangement of glowing points, each one separated by light years, yet together forming a contour that spans cosmological scales. A quiet scientific mystery lies in the question of whether the Sloan Great Wall should be considered a single structure at all. Some analyses suggest it is too large to form through gravitational collapse alone, raising questions about whether its apparent continuity is partly the result of projection effects or sampling patterns. Other studies indicate that it may not be gravitationally bound in the classical sense, but instead represents a segment of the cosmic web where the density of galaxies happens to peak. The boundary between a true structure and a statistical feature remains subtle and is not yet settled. This uncertainty reflects the complexity of defining objects at cosmic scales, where distances exceed comprehension. Three soft ironies accompany the discovery of the wall. The first is that such a large structure becomes visible only after billions of years of cosmic history, yet it was present long before any observer existed to detect it. The second is that its vastness is composed entirely of empty space, with galaxies spaced so far apart that a traveller moving at the speed of light would take millions of years to cross from one cluster to the next. The third is that what appears solid and continuous in a map is in reality a thin arrangement of islands suspended in a sea of near emptiness. The wall's outer form takes shape when clusters within it are identified. These clusters hold thousands of galaxies, each bound by their mutual gravitational attraction and the presence of dark matter halos. Between them, thinner bands of galaxies connect the clusters, forming bridges that give the appearance of continuity. These bridges, though sparser than the clusters, still play a key role in defining the overall structure. Without them, the wall would fragment into separate pieces, each one less remarkable than the whole. The distribution of these galaxies creates the impression of a wall, though it is more accurately described as a chain of clusters and filaments. Another accepted detail concerns the role of dark matter in shaping the wall. The filament owes its existence to the underlying distribution of this unseen mass, which forms a scaffold that guides the flow of gas and galaxies. Simulations of the early universe predict that dark matter forms long thread-like structures where normal matter collects. Observations of the Sloan Great Wall confirm this prediction, showing that the galaxies within it follow paths defined by dark matter's gravitational pull. The alignment of clusters and bridges reflects the invisible skeleton beneath them. A poetic detail emerges in the faint bridges that connect the clusters. These bridges contain galaxies so widely separated that their combined light appears as a gentle haze when mapped. Their distribution is subtle, yet without them the wall would not form a continuous feature. The filaments are like strands of vapour stretched between heavier knots, delicate yet essential. Their faintness reveals the structure through absence as much as presence. A quiet mystery persists in how these filaments formed. While models predict their development, the precise initial conditions that create such an extended feature remain uncertain. The earliest density fluctuations varied across space, but how these variations aligned to produce such a long filament is still a matter of study. Whether the wall represents a rare coincidence or an expected outcome of cosmic evolution is not fully settled. Some aspects of its symmetry and length challenge current understanding. The three soft ironies of this region continue. Only took the entire age of the universe for matter to settle into a pattern that resembles a wall. Only took the collective gravity of billions of stars to hold clusters together, yet their light forms only a thin line in the sky. Only took a fraction of cosmic history for humans to discover it despite its enormous scale and ancient presence. The Sloan Great Wall sits between major voids whose emptiness outlines the wall's boundary. These voids stretch across hundreds of millions of light years, amplifying the contrast between dense and empty regions. The shapes of these voids, smooth and rounded, suggest that matter flowed out of them during the universe's early evolution, collecting along the edges where the filaments lie. This relationship between voids and filaments defines the architecture of the cosmic web. As the narrative remains firmly within the outer region of the Great Wall, the next step will move inward, following its contour toward the clusters embedded within it. The wall's outline has now taken shape, and the story will gradually narrow into its internal components. The Sloan Great Wall stretches across a region where galaxies gather into a filament so long and coherent that its scale exceeds the imagination by many degrees. At this stage in the inward progression, the narrative remains focused on the wall's full outer contour, its reach, its boundaries, and the extended filament that connects one cluster to another across hundreds of millions of light years. This filament forms one of the universe's largest continuous patterns. Although it is composed of discrete galaxies separated by immense distances, its collective structure presents a unified shape, each point contributing to the extended spine of the wall. A scientifically accepted fact establishes the scale. The Sloan Great Wall spans nearly 1 billion light-years in length when measured along its longest axis. This enormous distance includes multiple clusters and groups of galaxies, each forming a local region of density within the greater filament. The filament itself is thin compared to its length, with its thickness only a small fraction of its full span. This disproportionate geometry, immense length, delicate width, is a hallmark of the cosmic web. Filaments act as channels along which matter flows, linking denser regions and outlining the structure of the early universe. Over billions of years, gravitational attraction encourages matter to settle into these paths, strengthening the filament while voids expand around it. A poetic detail emerges in the faintness of the filament's extended edges. At the limits of the wall, the density of galaxies decreases until only a few remain to mark the outer boundary. These distant galaxies shine softly, their light stretched by deep cosmic expansion, until it arrives as a thin signal barely distinguishable from background glow. Yet each galaxy plays a role in defining the filament's edge, its position adding a point to the map that reveals how far the structure extends. The faintness contrasts with the brighter clusters nearer the wall's center, creating a gradient of density that allows the filament to be traced with careful measurement. A quiet scientific mystery lies in the filament's remarkable coherence. Standard cosmological models predict filaments, but structures approaching the Great Wall's length have prompted questions about the exact mechanisms behind their formation. Did the early universe contain density variations aligned in such a way that an extended filament naturally emerged, or is the wall an unusual feature formed through a rare combination of factors? Some simulations reproduce similar features, while others suggest that such a long structure may challenge certain assumptions in cosmology. Whether the wall represents a typical filament or an outlier remains uncertain, and the nature of its origin continues to be studied. 3 soft ironies arise from contemplating the filament's full length. The first is that a structure so vast that it spans nearly 1 billion light-years is composed of galaxies that rarely, if ever, interact with one another. Their separation remains too great for gravitational encounters within human timescales. The second irony is that the filament appears continuous in maps, yet is mostly empty space with galaxies occupying only a minute fraction of its volume. The third is that such a large structure becomes visible only when viewed from enormous distance. Up close, it would appear as scattered points with no coherent shape. As the narrative traces the filament, it becomes clear that its length serves as both a boundary and a skeleton for the surrounding cosmic web. On one side lie expansive voids, where matter is scarce, forming regions nearly devoid of galaxies. On the other side, smaller filaments feed into the Great Wall, branching like tributaries into a main river. These smaller filaments bring additional matter into the wall, contributing to its density and shaping its internal structure. Although the focus remains on the outer contour, these tributaries quietly hint at the complexity that will be explored in future sections. A scientifically grounded detail concerns the flow of matter along the filament. Over billions of years, gas and dark matter drift gradually toward the densest regions of the wall. This slow movement driven by gravity thickens the filament and builds the clusters embedded within it. Although galaxies move within the wall, their overall positions remain relatively stable on cosmic timescales. The flow is gentle, more like a gradual rearrangement than a dynamic collision. This behavior reflects the calm tone of the universe at large scales where motion is measured in millions of years rather than moments. One poetic detail appears in the distribution of star-forming galaxies along the filament. In some regions, clusters of blue galaxies mark active formation, while in others the population consists mainly of older redder galaxies that formed their stars long ago. This variation gives the filament a textured appearance when mapped in colour, despite its distant faintness. The presence of star-forming regions adds subtle depth to the wall's contour, indicating the life cycles of galaxies within its structure. A quiet mystery persists regarding the thickness of the filament. While simulations predict a range of possible thicknesses for large filaments, the Great Wall's dimensions suggest a particularly narrow structure surrounding a dense core. Whether this narrowness reflects early conditions, gravitational interactions, or later evolution is not fully understood. The thinness may indicate efficient matter, flow toward the centre, or it may result from initial density contrasts that shape the filament's growth. Three more ironies rest softly within this context. Only took the entire expansion history of the universe for the filament to settle into its shape, yet its thickness remains only a fraction of its length. Only took countless generations of stars to illuminate its structure, yet their light arrives as faint signals barely visible from Earth. Only took the gravitational pull of dark matter to guide its formation, yet dark matter remains unseen and inferred only from motion. The filament's full outer contour now forms a continuous arc across the sky when transformed into a three-dimensional map. Its length sets it apart from neighbouring structures, creating a spine that divides regions of different density. As the narrative prepares to move inward, the filament's large-scale geometry is now clear, a thin extended structure connecting clusters and bridging the voids around it. The next section will explore the clusters embedded within this structure, moving one step inward from the outer boundary to the dense regions that anchor the wall. The Sloan Great Wall contains several major clusters embedded along its immense length, each one acting as a gravitational anchor within the larger filament. At this stage, the narrative moves one step inward, shifting from the wall's outer contour to the dense nodes where thousands of galaxies gather into coherent systems. These clusters mark the wall's internal structure, forming the backbone of its mass and shaping the flow of matter along the filament. Their presence defines the wall not merely as a chain of galaxies, but as a sequence of deep gravitational wells embedded within the cosmic web. A scientifically accepted fact provides the basis for this inward movement. Galaxy clusters are the largest gravitationally bound structures in the universe. Each cluster contains hundreds to thousands of galaxies, along with enormous reservoirs of hot gas and a dominant halo of dark matter. Within the Sloan Great Wall, these clusters lie spaced along the filament, forming bright concentrations that appear as knots in three-dimensional maps. They reveal the regions where matter has settled most deeply into the underlying dark matter scaffolding. These clusters do not merge into a single unit, but they remain connected through the filament's gravitational field. A poetic detail emerges in the glow of the intracluster medium, the gas that fills the space between galaxies. This gas, heated to tens of millions of degrees, emits soft X-rays that outline the clusters like faint halos. Although invisible to the eye, this radiation reveals the mass and structure of the cluster more clearly than the galaxies themselves. The glow is diffuse and continuous, a smooth background that contrasts with the sharp points of starlight. It gives each cluster a quiet luminosity that hints at the scale and density of its interior. A quiet scientific mystery surrounds the origins of the largest clusters within the wall. While simulations predict the formation of clusters in dense regions, some clusters in the Sloan Great Wall appear unusually massive for their location. Whether these clusters grew from early density fluctuations or acquired their mass through long periods of gentle merging remains uncertain. Their existence raises questions about how matter gathered along the filament during the universe's early evolution. The exact pathways that created such large structures still elude complete explanation. 3 soft ironies accompany the observation of these clusters. The first is that clusters contain enormous amounts of matter, yet the space between galaxies within them is mostly empty. The second is that clusters appear as bright, dense nodes in maps of the universe, but their internal regions span distances so great that galaxies can pass each other without interacting for billions of years. The third is that clusters seem permanent when viewed from afar, yet inside them, stars burn out, galaxies evolve, and gas cools in cycles that never stop shifting. The clusters along the Sloan Great Wall serve as gravitational hubs, drawing in gas and galaxies from surrounding filaments. These infalling galaxies follow paths determined by the complex gravitational landscape created by dark matter halos. Over billions of years, the clusters grow, gradually incorporating new members and expanding their mass. The presence of such clusters strengthens the overall filament, creating points of significant density that give the wall its recognizable shape. They define the rhythm of the structure-dense region, bridge-cluster bridge, and so on along the length of the wall. A scientifically grounded detail involves the motion of galaxies within these clusters. Galaxies orbit the cluster's center at speeds of hundreds of kilometers per second, held in place by the cluster's immense gravitational pull. Their paths are influenced by interactions with dark matter, the intracluster gas, and occasional close encounters with other galaxies. Despite these interactions, most galaxies maintain stable orbits, moving slowly through the cluster's potential well. These motions are not chaotic, but form a balanced long-term dance that reflects the cluster's mass distribution. A poetic detail appears in the color distribution of galaxies within clusters. The densest regions contain mostly old red galaxies whose star formation ceased long ago. Their uniform glow gives the cluster a muted appearance. In contrast, the outer regions of the cluster contain bluer galaxies that still form stars, adding subtle variations to the overall structure. The gradient of colors reveals the history of interactions, mergers, and the gradual quenching of star formation as galaxies move toward the cluster's center. A quiet mystery persists in the behavior of the intracluster medium. Although heated to extreme temperatures, this gas cools slowly through radiation. In some clusters, cooling should produce new stars at a high rate, yet observed star formation is lower than expected. The presence of energetic processes, possibly from supermassive black holes in central galaxies, may reheat the gas, but the exact mechanisms remain uncertain. This discrepancy, known as the cooling flow problem, continues to challenge models of cluster evolution. 3 more soft ironies accompany this deeper view. Only took billions of years for clusters to gather their mass, yet their internal motions appear calm and steady. Only took countless galactic interactions to create the muted colors of cluster cores, yet those interactions occur over spans too long for any observer to witness directly. Only took the invisible pull of dark matter to shape the entire cluster, yet dark matter itself remains undetected except through its influence. The clusters embedded within the Sloan Great Wall form the skeleton of the structure, providing points of density that anchor the filament. Their mass, temperature, and composition reveal the inner workings of the wall more clearly than any individual galaxy can. As the narrative continues to move inward, the next step will follow the structure from these clusters into the galaxies themselves, shifting from the large-scale gravitational wells to the smaller components that populate them. From the deep gravitational wells of the clusters, the narrative moves one step inward to the galaxies themselves, the fundamental building blocks that populate the Sloan Great Wall. Each galaxy represents a self-contained system of stars, gas, dust, and dark matter, bound together by gravity and shaped by billions of years of evolution. While clusters define the mass and structure of the wall at large scales, it is the galaxies that give the wall its observable form, their combined light tracing the filament across cosmic distances. The inward shift now focuses on these galaxies as individual components, examining their distribution composition and quiet rhythms within the greater filament. A scientifically accepted fact anchors this region. Galaxies in large-scale filaments like the Sloan Great Wall are not arranged randomly, but follow the flow of matter along the filament occupying positions, influenced by underlying dark matter halos. These galaxies come in various forms: spirals, ellipticals, lenticulars, each reflecting a different history of formation and interaction. Spiral galaxies typically populate the less dense regions of the filament, where tidal forces are weaker and gas remains abundant. Elliptical galaxies tend to cluster near the densest nodes, having formed through mergers and interactions that erase their original structure. This diversity gives the filament a layered texture when observed across different wavelengths. A poetic detail appears in the glow of spiral galaxies whose arms hold clusters of young blue stars. These stars shine brightly against the dark backdrop of intergalactic space, creating soft spirals of light that record the movement of gas and the gentle pull of gravity over billions of years. In contrast, elliptical galaxies give off a warm, diffuse light composed of older stars. Together, these galaxies form a mosaic that illuminates the length of the filament, their combined radiance outlining the shape of the wall from edge to edge. A quiet scientific mystery lies in the role that environment plays in shaping galaxy evolution within such large structures. While it is known that galaxies near the dense centers of clusters tend to lose gas and cease forming new stars, the precise mechanisms that govern this process along the filament are still uncertain. Some galaxies quench their star formation, despite lying far from cluster centers, suggesting that even the filament itself exerts environmental influence. Whether this quenching results from interactions with thin streams of gas gravitational tides or ancient conditions from the early universe remains an open question. The variation in star formation across the filament hints at a complex interplay of factors not yet fully understood. Three soft ironies accompany the contemplation of these galaxies. The first is that galaxies appear as bright dots in cosmic maps, yet each contains billions of stars enough to form intricate structures that remain invisible at such distances. The second is that galaxies shape the appearance of the filament, even though the filament's true structure is defined by the dark matter that cannot be seen. The third is that galaxies evolve over spans of time so long that even dramatic events such as mergers or starbursts unfold slowly enough to seem serene when viewed on cosmic scales. A scientifically grounded detail centers on the dark matter halos surrounding each galaxy. These halos extend far beyond the visible regions, forming a protective sphere that governs the galaxy's rotation and stability. Observations show that the velocities of stars within galaxies cannot be explained by visible matter alone. Dark matter provides the additional gravitational pull needed to maintain their structure. Within the Sloan Great Wall, these halos nest inside larger halos belonging to groups and clusters, forming a hierarchy of gravitational influence. This nested arrangement shapes the distribution of galaxies along the filament. A poetic detail emerges in the thin streams of gas that connect galaxies within the filament. These streams, nearly invisible, act as conduits for material, allowing gas to flow between systems over millions of years. While faint, they support star formation by replenishing galaxies with new material. Their presence adds subtle texture to the filament, forming delicate threads that bind galaxies into a coherent sequence. Though invisible to the eye, they shape the long-term evolution of galaxies across the wall. A quiet mystery persists in the distribution of dwarf galaxies along the filament. These small, faint systems are difficult to detect, yet they contribute significantly to the total number of galaxies. Their origins remain debated. Some may form within the filament itself, condensing from small pockets of gas. Others may be fragments of larger galaxies torn apart by tidal interactions. Their presence reveals the dynamic processes occurring within the filament, even if the details remain uncertain. Three soft ironies return in this context. Only took billions of years for galaxies to form and arrange themselves along the filament, yet their current positions appear static when viewed from Earth. Only took the light of countless stars to illuminate the wall, yet that light arrives as faint points that fade quickly in the brightness of the night sky. Only took the invisible framework of dark matter to hold these galaxies together, yet the true form of that framework will never be directly observed. As the narrative continues inward, the focus narrows from galaxies as objects to the stars, gas and dust that define their inner structures. The galaxies within the Sloan Great Wall serve as the visible markers of an immense filament, but their internal composition reveals even more about how the wall formed and evolved. The next section will shift gently into these galactic interiors, following the structure from environment to material, and observing the processes that shape the visible components of the universe. Inside the galaxies that trace the Sloan Great Wall, starlight threads through disks, bulges and halos, revealing how matter organizes itself at scales much smaller than the filament, yet still guided by the same gravitational framework. The narrative now moves further inward, staying within the galactic interiors, while keeping their place in the wall in view. Each galaxy is a luminous knot within the filament, its internal structure shaped by the balance of stars, gas and dark matter, that together decide how it spins, shines and endures. The filament sets the context, but it is within these galaxies that light is generated, processed and released into the vast spaces between clusters. A scientifically accepted fact anchors this inward step. The bulk of visible light in the universe comes from stars bound within galaxies, while the overall motion and stability of those galaxies are dominated by their dark matter halos. Stars trace the visible structure, gas regulates future star formation, and dark matter defines the gravitational well that holds both in place. Within the Sloan Great Wall, this triad shapes not only each galaxy's internal arrangement, but also its position and behavior within the filament. In spiral galaxies along the wall, thin disks of stars orbit within flattened planes, supported by rotation. Their light forms arcs and arms that wrap gently around the center, marking regions of higher density, where gas clouds compress and form new stars. Young massive stars emit bright blue and ultraviolet light, while older stars in the bulge glow with softer red and yellow tones. The blend gives each spiral a layered appearance, a quiet gradient from bright star-forming arms to older, more settled interiors. Embedded within and beyond this luminous disk is a wider halo populated by older stars and globular clusters, extending far into the surrounding dark matter halo. The rotation curve of such a galaxy remains flat at large, radii a measured fact that indicates the presence of unseen mass. Dark matter dominates the outer regions, ensuring that stars in the outskirts remain bound despite their high orbital speeds. A poetic detail appears in the way starlight diminishes with distance from the galactic center, but never truly ends, fading gradually into the halo. Along the length of the Sloan Great Wall, countless such halos overlap only statistically, not physically, creating a continuous but non-contacting series of luminous and dark envelopes that track the filament's spine. In elliptical galaxies within the wall, stars move in more random orbits, lacking the ordered rotation seen in spirals. Their light forms smooth, rounded profiles brightest at the center, and gradually fading toward the edges. These galaxies often reside near cluster cores, where interactions and mergers have reshaped their structure. Gas in these systems is sparse or heated, limiting new star formation. As a result, their light is dominated by older stars, giving them a uniform warm hue. Dark matter halos surround them as well, but their influence appears in the distribution of stellar velocities rather than in rotation curves. The balance between these stars and their halos ensures that the elliptical galaxies retain their shape and remain anchored within the larger gravitational environment of the cluster and the filament. A quiet scientific mystery lingers in how precisely the dark matter distribution within halos relates to the properties of the galaxies they host. Empirical relations such as those linking stellar mass rotation, speed, and halo concentration are well measured, yet the underlying reasons for their tightness remain under investigation. Simulations reproduce broad trends, but sometimes diverge in detail, suggesting that baryonic processes such as feedback from star formation and central black holes modify halos in ways not yet fully captured. Within the Sloan Great Wall, the consistency of galactic properties along the filament hints at a shared formation environment, yet local variations show that each galaxy carries its own detailed history superimposed on that common framework. Three soft ironies arise when considering how starlight threads through these filament galaxies. The first is that the stars which provide nearly all observable light contribute only a small fraction of each galaxy's total mass, with gas and especially dark matter supplying the rest. The second is that the visible structure of disks, bulges and halos is shaped heavily by unseen components whose presence is inferred only through motion. The third is that the patterns of stars that seem most striking to observation, such as spiral arms and central bars, are transient on long time scales, while the dark matter distribution, which remains unseen, persists more stably. Within each galaxy of the wall, gas plays a central role in linking environment to internal structure. Cold gas collects in disks, forming reservoirs from which molecular clouds condense. These clouds collapse under self-gravity to form new stars, particularly in regions where density is slightly higher, such as spiral arms or bars. In galaxies closer to cluster centers, interactions with hot intra-cluster gas strip away some of this cold gas through processes such as ram pressure, reducing the fuel available for star formation. This environmental influence creates gradients along the filament galaxies near dense nodes, exhibit less active star formation, while those farther out retain more gas and continue forming stars at higher rates. Over time, this leads to a quiet variation in colour and luminosity along the wall. A scientifically grounded detail concerns the way dark matter, halos of galaxies within the wall, respond to the larger scale potential of the filament. Halos do not exist in isolation. They reside within an extended dark matter structure that stretches along the wall's length. As a result, the shapes of halos can be slightly elongated along the filament, and their orientations may correlate with the direction of the wall. This alignment influences how gas accretes onto galaxies, often guiding inflows along preferred directions. The result is a subtle coherence in the way disks are oriented and how angular momentum is acquired, linking galactic spins to the geometry of the superstructure. A poetic detail appears in the concept of cold gas streams flowing along the filament into galactic halos. These streams, too diffuse to be directly imaged in most cases, deliver fresh material that can cool and settle into rotating disks. The process is slow unfolding over billions of years, yet it maintains star formation in galaxies far from the densest cluster cores. In this way, the filament acts as both support and supply route, passing material inward, while the galaxies convert it into starlight. A quiet mystery remains in the efficiency of this process. Not all galaxies along the wall show high rates of star formation even when gas appears available. Feedback from supernovae and central black holes may heat or expel gas, preventing it from cooling efficiently. The degree to which large-scale environment versus internal feedback governs this balance is unsettled, and observations continue to refine the picture. Three soft ironies close this level of the inward journey. Only took small variations in early density fields to create the dark matter scaffolds that now dominate galactic structure. Only took thin disks of gas to arrange billions of stars into organized patterns that trace the filament's outline. Only took the faintest fraction of total mass shining as starlight to reveal the presence of an overwhelming invisible framework. Within the galaxies of the Sloan Great Wall, stars, gas and dark matter combine to produce systems that are individually complex yet collectively ordered along the filament. Their internal structures arise from local physics, while their positions reflect the large-scale geometry of the cosmic web. Having moved into these galactic interiors, the narrative will next narrow further from the arrangement of stars and gas into the specific regions where new stars are born within the wall's galaxies, following the path from environment to material, and then to the smaller scales of physical process. Inside the filament galaxies of the Sloan Great Wall, cold gas settles into rotating structures that act as the immediate reservoir for future stars, tying the large-scale environment of the wall to the small-scale processes that unfold inside each system. The narrative now moves inward from the broad arrangement of stars and halos to the materials that support ongoing star formation, neutral hydrogen molecular gas, and the dust grains mixed through them. These components collect in disks that move as coherent, slowly spinning patterns, flattened by angular momentum and contained by gravity. The wall provides the geometric context and the supply routes along which gas flows. The galaxies translate that gas into luminous structure. This section remains firmly at the level of galactic materials and motions, holding close to the environment of the wall while stepping away from individual stars and not yet entering the microphysics of the clouds themselves. A scientifically accepted fact sets the frame for this level of detail. In star-forming galaxies, cold gas resides primarily in extended disks composed of neutral hydrogen and molecules such as molecular hydrogen, with temperatures low enough that atoms and molecules move at relatively modest speeds compared with the hotter halo gas. These disks often stretch well beyond the visible stellar component, forming wide, faint halos of gas that continue far into the outskirts of a galaxy. In the galaxies of the Sloan Great Wall, observations show that such gas disks align with the overall rotation of the system, and often follow the direction of the filament itself, hinting at the way gas accretes along large-scale structures. Rotation curves reveal that this cold gas orbits the galactic centre at nearly constant speed over a broad range of radii, reflecting the influence of dark matter halos. The gas, though diffuse, responds to the combined gravitational pull of stars' dark matter and its own mass settling into a configuration where inward pull and outward centrifugal tendency balance. A poetic detail appears in the outer reaches of these gas disks where starlight becomes faint, but the neutral hydrogen continues forming extended, nearly invisible layers that emit only weak radio signals. In some galaxies along the wall, the gas disk can be several times wider than the luminous disk, creating a quiet halo of material that orbits in darkness, awaiting the conditions needed to condense into denser regions. These outer disks trace the gravitational reach of the galaxy more clearly than the light from its stars and provide a smooth continuation of the rotation curve into regions where almost no starlight is present. Along the filaments, such extended gas structures overlap statistically in distance, so that when projected onto a large-scale map they form a continuous though sparse sea of cold material threading through the wall's length. A quiet scientific mystery lies in the efficiency with which this cold gas converts into stars along different parts of the filament. Some galaxies in the Sloan Great Wall show high surface densities of gas, but only modest rates of star formation, while others with similar gas content exhibit more active stellar birth. This variation persists even after accounting for differences in mass and morphology. It raises questions about how subtle environmental factors, such as tidal fields from nearby clusters, low-level heating from the intergalactic medium or past interactions, might regulate the stability of gas disks. Whether the large-scale position within the wall changes the threshold at which gas becomes gravitationally unstable remains under study. Simulations suggest that filaments can feed galaxies through cold flows that vary in strength over time, but the detailed connection between these flows and local star formation has not been fully resolved. Three soft ironies accompany this level of structure. The first is that the coldest gas, which contains the least thermal energy, plays the most vital role in shaping a galaxy's future, providing the raw material from which new generations of stars emerge, while itself remaining almost completely dark. The second is that the most extended components of galaxies, the outer neutral gas disks, are the ones least visible to human vision, yet they hold key information about the gravitational field and the angular momentum history of each system. The third irony is that these disks, which appear smooth and stable on large scales, are in reality delicately balanced with small perturbations capable of triggering waves, rings, and other structures that channel gas inward or outward over millions of years. A scientifically grounded detail concerns the internal motions within these rotating gas disks. While the overall movement is ordered, rotation local velocity dispersions introduce a small but important level of randomness. Gas clouds move relative to one another at speeds of several kilometers per second, enough to create shocks when they collide and compress, but not enough to disrupt the global disk. These motions are influenced by spiral density waves bars and interactions with satellite galaxies. Along the Sloan Great Wall, galaxies residing in slightly denser regions of the filament may experience more frequent gravitational nudges from neighbours subtly stirring their gas and altering the balance between support and collapse. Over time, this can change how and where stars form inside the disk, without altering the galaxy's overall position within the wall. A lesser-known observational detail appears in the way warps and flares develop in the outer parts of these gas disks. In many filament galaxies, the outer disk bends slightly above and below the main plane, forming a gentle warp that can be traced in radio maps. These warps often align with the direction toward neighbouring structures in the wall, suggesting that tidal forces from the filament and nearby groups may influence the outer gas. Flares, where the thickness of the gas layer increases with radius, indicate that the outer disk is less tightly bound and more easily disturbed. Together, warps and flares record the quiet history of interactions between each galaxy and its surroundings, storing information about the gravitational environment of the wall in the geometry of the gas itself. A quiet mystery persists in how long such warps endure. Some models propose that they are transient features that gradually damp out, while others indicate that continuous torques from the filament or from misaligned dark matter halos can sustain them over long timescales. The presence of widespread warps in disk galaxies along large-scale structures suggests that such torques may be common. Determining the relative importance of internal and external causes remains an active field of study linking the dynamics of cold gas to the larger question of how galaxies respond to their positions within the cosmic web. 3 additional soft ironies rest at this depth. Only took the faint gravitational pull of far-off structures to bend the outer gas layers of entire galaxies, yet those bends are measured through small shifts in radio emission. Only took the slow accumulation of gas over billions of years to build disks that appear simple and thin while their internal motions and shapes encode a complex history of flows and interactions. Only took a narrow temperature range to keep gas in the cold phase, yet small changes in heating or turbulence can move it out of this regime, altering the course of star formation on galactic scales. As the narrative remains within the region of cold gas and rotating disks, it becomes clear that these structures serve as the intermediate layer between the large-scale environment of the Sloan Great Wall and the small-scale sites where stars actually form. The disks collect material from the filament, redistribute it through rotation and local motions, and gradually funnel it into denser pockets where further processes can act. Having now described the materials and motions that prepare gas for star formation, the next inward step will move into those denser regions within the disks, where dust molecules and cooling combine to form the clouds that eventually collapse into new stars while still remaining within the same galaxies that trace the wall's long filament. Within the cold, rotating disks of the galaxies that line the Sloan Great Wall, the narrative moves inward again, shifting from the broad flows of atomic gas to the denser, more complex regions where molecules form, dust accumulates, and the groundwork for starbirth takes shape. These inner layers mark a transition from diffuse material, influenced primarily by gravity and rotation, to structures governed by cooling chemistry and local variations in density. The path remains strictly inside the same region galactic interiors, yet narrows to the physical ingredients that give rise to the next stage of structure. Dust grains, molecular clouds, and elemental mixtures form a quiet interior landscape that traces the conditions of star formation across the length of the wall. A scientifically accepted fact anchors this level. Molecular clouds compose the coldest, densest phase of the interstellar medium in star-forming galaxies. These clouds consist primarily of molecular hydrogen, accompanied by helium and small fractions of heavier elements. However, molecular hydrogen, being symmetric, does not emit strongly under cold conditions, so astronomers detect molecules like carbon monoxide as proxies for the larger molecular reservoirs. Observations of galaxies along filaments show that these clouds often concentrate along spiral arms bars and regions where gas flows converge. Their presence indicates where the interstellar medium has cooled enough for molecules to form and survive. Dust grains composed of carbon-rich compounds and silicates play an essential role, providing surfaces on which hydrogen atoms combine into molecules. Without dust, the molecular phase could not form efficiently under typical galactic conditions. A poetic detail lies in the way dust dims and reddens the starlight passing through it, giving dense regions a muted glow when viewed in optical wavelengths. These quiet shadows, subtle and soft-edged, outline the positions of clouds, even when the clouds themselves remain invisible. In galaxies of the Sloan Great Wall, dust lanes trace the inner curves of spiral arms, forming dark ribbons that run across bright star fields. At longer wavelengths, these same lanes glow faintly as dust grains absorb starlight and re-emit it as infrared radiation. The contrast between their darkness in visible light and their gentle warmth in infrared creates a dual portrait of the same material depending on the observer's vantage and instruments. A quiet scientific mystery remains in how the distribution of molecular gas varies along the length of the wall. Surveys show that some galaxies embedded deeply in the filament host-rich reservoirs of molecular clouds, while others in similar environments contain much less. Even after accounting for differences in stellar mass and morphology, variations persist. Whether these differences reflect the local cosmic web density, subtle tidal fields, or ancient formation histories is uncertain. Some models suggest that galaxies near the densest nodes of filaments may have exhausted or heated their gas more rapidly in the past, leaving less raw material for present-day molecular clouds. Others propose that gas accretion from the filament may proceed unevenly depending on the orientation of a galaxy's halo relative to incoming flows. Three soft ironies accompany this interior view. The first is that dust, which makes up only a tiny fraction of galactic mass, controls the chemistry of the molecular phase by providing surfaces for molecule formation. The second is that molecular clouds, which appear stable and massive, are transient on cosmic timescales, drifting apart or collapsing within tens of millions of years, brief moments compared with the long, slow evolution of galaxies and filaments. The third irony is that the coldest, darkest regions within galaxies, those least visible to starlight, serve as the cradles of future brightness, setting the stage for star formation that will illuminate the filament for billions of years. A scientifically grounded detail concerns the internal structure of molecular clouds. These clouds are turbulent with motions far exceeding the sound speed of the cold gas. Despite temperatures only a few tens of degrees above absolute zero, the gas within these clouds exhibits velocity dispersions driven by turbulence, magnetic fields, and gravity. This turbulence prevents the cloud from collapsing immediately. Instead, it creates nested regions where denser pockets form through converging flows. Over time, these pockets become gravitationally unstable, eventually collapsing into protostars. The balance between turbulence, cooling, and gravity determines how rapidly molecular clouds convert gas into stars. Galaxies along the Sloan Great Wall exhibit a full spectrum of such efficiencies, hinting again at subtle environmental influences that shape the molecular phase. A poetic detail appears in the quiet glow of polycyclic aromatic hydrocarbons complex molecules that emit faintly in the infrared when excited by ultraviolet starlight. These molecules outline regions near molecular clouds, forming diffuse halos of emission that soften the transition between star-forming and quiescent areas. Though invisible in most wavelengths, they reveal the gentle interplay between young stars and the molecular reservoirs that surround them. Along the filament, these emissions create faint textured patterns that echo the distribution of clouds arranged within each galaxy. A quiet mystery persists in whether the filament's large-scale structure influences the chemical evolution of its galaxies. Some studies indicate that galaxies in dense cosmic web environments show slightly enhanced metallicities at fixed stellar mass, suggesting more efficient recycling of enriched gas, or earlier formation times. Whether this trend holds across the various segments of the Sloan Great Wall remains an open question. If confirmed, it would imply that the position within the cosmic web leaves subtle imprints on the chemical makeup of galaxies shaping dust, abundance cooling rates, and the conditions for molecular cloud formation. 3 additional soft ironies drift through this molecular landscape. Only took small grains of dust to catalyze the formation of molecules that control the fate of entire galaxies' star-forming potential. Only took slight variations in density and temperature to produce clouds of enormous mass, yet these clouds remain vulnerable to disruption by modest turbulence. Only took faint infrared emissions to reveal the presence of complex organic molecules scattered across galactic disks, yet these molecules represent only a tiny fraction of the total mass. Within these molecular and dusty regions, galaxies of the Sloan Great Wall prepare the raw material for the next step in the inward progression. The dark lanes visible across their disks mark the densest reservoirs of gas, while the turbulent interiors of clouds determine where stars will eventually form. All these processes unfold within the same galaxies whose combined light traces the filament structure. The narrative remains focused on this layer of material and chemistry, not yet advancing to the microscale processes of protostellar collapse. Those details belong to the next inward region. At this stage, the Sloan Great Wall reveals itself not only as a vast filament of galaxies, but also as a network of cold gas, dust and molecules distributed through those galaxies. This material represents the bridge between large-scale cosmic structure and small-scale astrophysical processes. As the path continues inward, the next section will move into the densest cores of these molecular clouds, observing how matter transitions from diffuse gas to collapsing structures that will eventually ignite as stars, always within the same whisper-soft contemplative tone. Deep inside the molecular clouds that drift through the disks of galaxies in the Sloan Great Wall, the gas and dust that once seemed smooth and continuous now reveal a structure that is fine-grained, clumpy and intricate. The narrative moves inward again, staying within these clouds and focusing on the densest cores where gravity begins to overcome the opposing support of turbulence, magnetic fields and thermal pressure. In these regions, the connection between the large-scale filament and the smaller scales of astrophysical structure becomes clear because the same material that once flowed along the vast dark matter spine of the wall now gathers into compact knots only a few light-years across. A scientifically accepted fact frames this level star formation in galaxies occurs predominantly within dense cores inside molecular clouds, where the gas reaches densities many orders of magnitude higher than the average interstellar medium, and temperatures low enough that molecular motions are slow and radiative cooling is efficient. These cores represent the innermost layer of structure in the path that began at the scale of the cosmic web, and within them gravity finally gains the upper hand. As density increases, the core becomes optically thick to its own cooling radiation, and the gas begins to collapse inward, more rapidly conserving angular momentum and forming a flattened, rotating configuration around a central protostellar object. A poetic detail appears in the way these cores remain invisible in ordinary light, while shining faintly in millimeter and submillimeter wavelengths. Instruments tuned to these long wavelengths can see through the dust that hides the cores, revealing compact peaks of emission that mark the locations where collapse is underway. In images of galaxies that lie along the Sloan Great Wall, these compact sources scatter along spiral arms and dust lanes like small cold embers, each one an isolated site where the quiet inward pull of gravity reshapes gas that has travelled across cosmic distances. A quiet scientific mystery remains in how efficiently these dense cores convert their mass into stars. Observations show that only a small fraction of a cloud's mass ends up in long-lived stars, with the rest dispersed back into the interstellar medium by feedback from radiation winds and eventual supernova. Yet the details of this regulation are not fully settled. Some simulations suggest that magnetic fields thread the cores and slow their collapse, while others point to turbulence that continually reshapes the density distribution. Measurements across many galaxies, including those in filamentary environments, reveal a roughly similar relationship between gas surface density and star formation rate, but the scatter around this trend and its dependence on local conditions remain subjects of study. Within the Sloan Great Wall, the degree to which the filament's large-scale potential influences core lifetimes fragmentation, patterns, or typical stellar masses is not yet known with precision. The path from cold cloud to collapsed star retains uncertainties even after decades of observation. 3 soft, quiet observations sit within these cores. It has taken billions of years for gas to flow along the filament into galaxies, yet the actual collapse of an individual core into a protostar unfolds over spans of only a few 100,000 years, a brief interval in cosmic context. It has taken the coordinated gravity of an entire wall of structure to deliver material to these clouds, yet the decision about which pockets collapse and which remain diffuse is governed by tiny local imbalances of density and motion. It has taken the slow global settling of the cosmic web to outline the Sloan Great Wall, yet the most luminous future contributions from this structure will arise from regions so small that no large-scale map can resolve them directly. Within a collapsing core, the gas flows inward while shedding angular momentum through interactions with magnetic fields and surrounding material. The result is the formation of a flattened envelope and a small, rotationally supported disk around the central protostar wherein falling material gradually spirals inward. Outflows and jets launched along the rotational axis by magnetohydrodynamic processes carry away excess angular momentum and energy, carving narrow cavities through the surrounding dense gas. These processes are widely observed in nearby star-forming regions and are understood as essential components of core collapse. In galaxies along the Sloan Great Wall, similar phenomena are expected to occur on a vast number of sites simultaneously, though individual outflows remain far too small to influence anything beyond their immediate surroundings. The cumulative effect, however, stirs the interstellar medium, injecting momentum and heat that will later help set the conditions for future generations of clouds and cores. A lesser-known detail arises from measurements of core mass distributions in different galactic environments. Studies indicate that the distribution of core masses bears a resemblance to the initial mass function of stars, suggesting that the way cores fragment inside molecular clouds may play a primary role in determining the masses of the stars that form. Whether this resemblance holds with the same precision in galaxies dense within filaments and walls as it does in more isolated systems is not yet fully tested, because observing cores at such distances remains challenging. If confirmed, it would imply that small-scale physics within clouds is remarkably robust to changes in large-scale environment, allowing stars and galaxies of the Sloan Great Wall to share similar mass distributions with those in less crowded regions of the cosmic web. A quiet mystery persists in the extent to which environmental pressure from the filament and cluster potentials sets the surface densities at which clouds can form and remain bound. Higher external pressure may allow clouds in certain parts of the wall to reach higher internal densities before feedback disperses them, potentially changing the fraction of mass that ends up in dense cores. Simulations that attempt to include both filamentary structure and detailed cloud physics are ongoing, and results suggest that while local turbulence and magnetic fields are decisive, the background pressure and shear from the large-scale environment provide boundary conditions that cannot be ignored. 3 more soft observations rest at this scale. Only modest variations in turbulence level can lengthen or shorten the lifetime of a dense core by significant factors quietly shifting the number of stars that eventually emerge. Only small differences in metallicity, which trace the prior generations of stars in a galaxy, can alter cooling rates enough to change how readily gas can collapse, linking chemical history to present structure. Only slight changes in the strength and orientation of magnetic fields can tilt the balance between support and gravity-altering fragmentation patterns without leaving obvious signatures on larger scales. At this depth of the inward journey, the connection between the Sloan Great Wall and the interiors of its galaxies becomes a matter of continuity rather than scale. The same gas that flows down filaments into halos gathers into disks, cools into clouds, and condenses into molecular complexes now collects in cores where its final collapse into stars is decided by local physics. The wall does not dictate the exact outcome of any individual core, yet it sets the mass supply, the background pressure, and the statistical conditions under which these cores arise. The narrative remains within this region of dense gas and protostellar collapse, completing the view of how matter progresses from diffuse cosmic structure to compact luminous sources. The next inward step will move still further down the chain of scale, entering the microphysical regime of the material itself, where the properties of atoms, ions, and dust grains define the cooling rates, opacities, and energy exchanges that regulate every stage described so far, all within the same galaxies that quietly mark the length of the universe's vast wall. Gravity works quietly through every layer of the Sloan Great Wall, from the largest stretches of filament down to the smallest collapsing cores inside molecular clouds, and this section remains within the same physical setting, while shifting inward to the governing mechanism that links all these scales. In the broadest view, gravity draws matter into the long spine of the wall, holding galaxies and clusters along a thread that traces the underlying distribution of dark matter. On smaller scales, it binds clusters together, shapes the motions of galaxies, stabilizes rotating disks, gathers cold gas into clouds, and finally drives the collapse of dense cores into stars. The same force operates in each context, yet its expression changes with scale density and time, producing the layered structure that has been followed from the outer cosmic web into the interiors of galaxies. A scientifically accepted fact frames this region. Gravity is always attractive and acts on all forms of mass and energy, causing structures in the universe to grow from small initial fluctuations into the large patterns now observed. In the early universe, tiny overdensities in the distribution of matter begin to slow their expansion relative to the background. Over billions of years, these regions become filaments and clusters as matter falls inward. Along the Sloan Great Wall, this history is recorded in the way clusters sit at the junctions of filaments and galaxies, line the filament's length, occupying gravitational wells that deepen as more matter accumulates. The wall is not a solid object, but a connected field of gravitational potential, a contour where the pull inward is slightly stronger than in neighbouring regions. Within a cluster embedded in the wall, gravity holds together thousands of galaxies and a vast amount of hot gas. The galaxies move within the cluster at high speeds, yet they remain bound because the total mass provides enough gravitational pull to prevent them from escaping. The cluster reaches a state known as virial equilibrium, where the average kinetic energy of its members balances their gravitational binding energy. This balance gives the cluster a stable structure over long time scales, even though individual galaxies follow complex orbits. A poetic detail lies in the fact that the hot gas between the galaxies, heated by falling into the cluster's potential, well carries a record of that gravitational depth in its temperature. The higher the temperature, the deeper the well. In this way, gravity imprints its strength on the energy of the intracluster medium, turning invisible curvature into measurable heat. A quiet scientific mystery persists in the exact distribution of mass within these wells. While the overall gravitational potential can be inferred from galaxy motions and gas temperatures, small deviations from simple models hint at substructure clumps of dark matter, remnants of earlier mergers, and slight asymmetries in the mass distribution. These features suggest a history of gradual assembly, yet disentangling the history from present observations remains difficult. Simulations provide guidance, but each cluster in the Sloan Great Wall carries its own unique sequence of infall and interaction, written into the way gravity has shaped it over time. Moving inward to individual galaxies, gravity governs the balance between rotation and collapse. A galaxy's rotating disk exists because angular momentum counters the inward pull of gravity, preventing the gas and stars from falling straight into the centre. The rotation curve, which remains nearly flat at large radii, reveals that mass is not concentrated only in the luminous regions, but is distributed in an extended halo dominated by dark matter. Here, gravity acts as both sculptor and support, drawing matter into the halo, and then allowing the disk to form where centrifugal support balances the inward pull. The disk's thickness reflects the balance between vertical gravity and the random motions of stars and gas. Thin disks indicate strong vertical gravity and relatively calm motions. Thicker disks point to past heating by mergers or interactions. In galaxies along the Sloan Great Wall, these balances vary with position and history, yet the underlying mechanism remains the same. A poetic detail appears in the gentle vertical oscillations of stars as they move through the galactic disk. Each star follows a path that carries it slightly above and below the midplane, bouncing in the gravitational field like a slow elongated wave. Over millions of years, these oscillations create patterns in stellar density that can be measured and used to infer the mass distribution in the disk and halo. In this sense, stars become traces of an invisible gravitational landscape, their orbits mapping out the shape of the potential in 3 dimensions. Within the cold gas disks described earlier, gravity plays a more delicate role. On large scales within the disk, self-gravity can cause the gas to become unstable when its surface density exceeds a certain threshold relative to its internal support. This instability leads to the formation of spiral arms bars and ring-like structures, which in turn concentrate gas into narrower regions. In those regions, gravity becomes stronger relative to turbulent and thermal support, allowing clouds to form. Yet the same gravitational instability that gathers gas into clouds can also stir the disk, generating waves and motions that oppose collapse elsewhere. The result is a self-regulating interplay where gravity both promotes and limits structure formation depending on location and time. A quiet mystery remains in how tightly this balance is maintained across different environments. Observations show that galaxies with very different histories still follow similar relationships between gas content and star formation rate, suggesting that gravity and feedback conspire to maintain a near-steady state. In the interiors of molecular clouds and their dense cores, gravity operates at its most concentrated scale within this path. Here the local gravitational potential wells are small in size but deep relative to the surrounding gas. As a core collapses, gravitational energy converts into heat and radiation, which escape through the surrounding material. If the cooling remains efficient, collapse continues. If cooling falters, pressure rises and can slow or halt the process. The precise interplay between gravity cooling and magnetic support determines whether the core forms one star, a small multiple system, or fragments into several objects. The densest parts of these cores trace the deepest local wells, and once a protostar forms, its gravity begins to dominate the immediate region, drawing in material from the collapsing envelope. 3 soft ironies emerge when gravity is viewed across all these scales. The first is that the same force that shapes the Sloan Great Wall across nearly 1 billion light-years also governs the fall of gas into a core only a few light-years wide, with no change in its fundamental description. The second is that gravity, though the weakest of the fundamental forces at the level of particles, becomes the dominant influence on the larger scales, because it never cancels and acts on all mass. The third is that the apparent stillness of large structures such as filaments and clusters hides a constant conversion of gravitational energy into heat motion and radiation, a slow, ongoing rearrangement that never truly stops. A scientifically grounded detail that links all these layers is the concept of gravitational potential energy. As matter falls into deeper wells, it loses potential energy, which appears as kinetic energy, thermal energy, or radiation. When gas flows along a filament into a cluster, its infall heats the intracluster medium. When a galaxy forms inside a halo, the settling of gas into the disk converts potential energy into rotation and turbulence. When a cloud collapses into cores, gravitational energy powers the emission that allows the collapse to proceed. In each case, gravity drives a flow from less bound to more bound states, allowing structures to assemble and evolve. A lesser-known subtlety is that the large-scale gravitational field of the filament and clusters sets boundary conditions for smaller structures without dictating their precise outcomes. The background potential influences pressures, shear, and tidal forces, which in turn affect how disks warp, how clouds form, and how cores collapse. Yet within those constraints, local physics introduces variation. Two galaxies in similar positions along the wall may have different star formation histories, not because gravity differs in principle, but because their detailed initial conditions and feedback histories diverge. Gravity provides the framework. Other processes fill in the specifics. As this inward examination of gravity concludes, the Sloan Great Wall can now be seen as a continuous structure in gravitational potential, extending from the broad spine of the filament down through clusters, galaxies, disks, clouds, and cores. The same force shapes every layer, guiding matter along paths that began as slight density fluctuations and developed into the larger structures in the observable universe. The narrative remains within this governing mechanism as the final step's inward approach, where the role of unseen mass becomes the focus and the hidden scaffold that defines the wall's shape is examined more closely. Beneath every visible part of the Sloan Great Wall lies an unseen scaffold, a distribution of dark matter that does not emit or absorb light, yet provides most of the gravitational pull that shapes the structure. This section remains within the same physical setting while shifting inward to the hidden mass that defines the wall's overall form. From the perspective of dynamics and structure, dark matter supplies the framework on which galaxies, clusters, and filaments assemble. The luminous matter traces this framework, but the underlying support comes from mass that interacts primarily through gravity. Without it, the long spine of the wall, the deep wells of its clusters, and the extended halos of its galaxies would not exist in their present forms. A scientifically accepted fact sets the scale of this component. Dark matter accounts for the majority of matter in the universe, far outweighing the ordinary atoms that form stars, gas dust, and planets. Its presence is inferred from galaxy rotation curves, gravitational lensing, and the motions of clusters. In systems along the Sloan Great Wall, these signatures are pronounced. Clusters embedded in the filament exhibit galaxy velocities and gas temperatures that require much more mass than the luminous content alone can supply. The same is true for galaxies lining the wall, whose flat rotation curves demand extended halos of unseen material. The mass of the wall is dominated by this invisible component, while starlight contributes only a thin layer overlaying the true distribution. A poetic detail appears in the way dark matter reveals itself through lensing. When light from distant background galaxies passes near the mass concentrations of the wall's clusters and halos, its path bends subtly. This bending distorts the shapes of the background galaxies, stretching them into faint arcs or slightly sheared forms. By measuring these distortions statistically across many lines of sight, astronomers reconstruct maps of the dark matter distribution. The result is a shadow-like image of the wall's underlying scaffold, where soft clumps and elongated ridges of mass emerge in regions where no direct light is seen. The visible galaxies become markers along this invisible relief, like small beacons tracing the ridges of a structure whose bulk lies hidden. A quiet scientific mystery persists at this depth. The true nature of dark matter remains unknown. Current understanding places it as a form of matter that interacts very weakly, if at all, with light and ordinary particles except through gravity. Searches for candidate particles continue in laboratories and observatories, yet no direct detection has occurred. Cosmological simulations that assume dark matter behaves as cold, collisionless particles reproduce large-scale structures such as filaments and walls with striking accuracy, yet some small-scale discrepancies remain, especially in the inner density profiles of halos and the abundance of low-mass substructures. Whether these differences arise from the physics of dark matter itself or from the complex influence of ordinary matter on halo structure is not fully resolved. The Sloan Great Wall, as a large-scale manifestation of the dark matter web, stands as both confirmation of the model and a reminder of its outstanding questions. Three soft ironies accompany this hidden scaffold. It has taken luminous matter to reveal the shape of something that does not shine, because galaxies and gas only gather where dark matter has already created potential wells. It has taken weak distortions in the images of distant galaxies to map a component that outweighs everything visible, using the smallest changes in shape to uncover the largest portion of mass. It has taken the dynamics of ordinary matter, which represents a minority contribution, to diagnose the distribution of the majority component that remains unseen. Within clusters along the wall, dark matter halos combine into extended structures that envelop the hot gas and galaxies. These halos overlap and merge as clusters grow, forming an irregular traxial mass distribution that extends beyond the visible boundaries of the cluster. The hot intracluster gas, which emits X-rays, settles into approximate equilibrium within this potential, its temperature and density gradients reflecting the shape of the dark matter halo. The galaxies move within this environment like test particles, their orbits mapping the deeper mass. In this way, three distinct tracers, gas temperature, galaxy velocity, dispersion, and weak lensing converge to describe the same dark scaffold that holds the cluster together and links it to the greater filament of the Sloan Great Wall. In individual galaxies, dark matter halos define the scale and stability of the disks and spheroids that form within them. The halos extend far beyond the luminous region, sometimes to radii 10 times larger than the visible disk. Their density decreases gradually with distance from the center, allowing stars in the outer parts of galaxies to orbit at roughly constant speed without drifting away. In galaxies along the wall, these halos are themselves nested within larger group and cluster halos, creating a hierarchy of gravitational structures. A lesser-known detail is that simulations suggest halos have a particular internal structure that follows characteristic profiles with densities that rise steeply toward the center and fall off more gently at large radii. Observations broadly support this behavior, yet the exact central slopes and the influence of feedback from stars and central black holes on halo cores remain active areas of comparison between models and data. A quiet uncertainty lies in the possibility that dark matter may possess additional properties beyond simple, cold, collisionless behavior. Some proposed models include slight self-interactions or different thermal histories that could alter halo shapes and substructure. On the scale of the Sloan Great Wall, such distinctions may be subtle, but on smaller scales they could affect the internal structure of halos, the abundance of small satellites, and the shapes of density profiles in cluster cores. Current measurements of clusters and galaxy groups within filaments continue to refine constraints on these properties, yet no definitive deviation has been confirmed. The wall thus acts as a laboratory, where the predicted dark matter web can be compared against observation testing the model's consistency across a wide range of scales. Three additional soft ironies emerge in this context. Only took a component that does not emit light to determine where nearly all light in the universe would eventually form by guiding gas and stars into its wells. Only took a framework completely transparent to ordinary radiation to shape the most visually striking patterns seen in deep surveys. Only took a substance that has not yet been identified in laboratories to become the standard explanation for the largest structures in cosmology. At this depth, the Sloan Great Wall appears as a long continuous region where the dark matter density is higher than average, forming a ridge in the cosmic web. The luminous baryonic structures, clusters, galaxies, gas trace this ridge but do not define it. Where the dark matter density peaks, clusters and groups arise. Where it falls, the wall's outline thins and eventually merges into the background web. The voids that border the wall correspond to regions where dark matter density is lower, allowing expansion to proceed more freely, and matter to flow outward toward filamentary ridges. In this sense, the wall and its surrounding voids are complementary expressions of the same underlying dark matter distribution. As the inward progression remains within the realm of dark matter, the continuity of structure from the cosmic web down to individual halos is now clear. The wall is not a separate object but a segment of a larger network defined by this component. Ordinary matter follows, cools, and condenses within that framework, creating the galaxies, clusters, and clouds already described. The physics of dark matter sets the stage for every subsequent process. With the scaffold now examined, the next step inward will move from the scale of halos and gravitational potentials to the microphysical properties of the ordinary matter that occupies them, focusing on atoms, ions, and radiation as they govern the detailed behaviour of gas and stars within this vast invisible backbone. Inside, the matter that gathers along the Sloan Great Wall structure continues downward from stars, clouds, and gas disks into the scale of atoms, ions, and radiation, where the detailed rules of microphysics control how energy moves and how matter changes its state. This section remains fully within that smallest inner region, describing how the properties of ordinary matter allow every larger layer of the wall to exist in its present form. At this depth, individual particles and photons determine whether gas cools or stays warm, whether clouds collapse or remain supported, and how light emerging from stars and hot gas carries information outward into intergalactic space. The large-scale filament, its clusters, and its galaxies now serve only as context. The focus rests on the local interactions that proceed in silence at every point within the structure. A scientifically accepted fact frames this level of description. The behaviour of ordinary matter in astrophysical environments is governed by the physics of plasmas, radiative processes, and atomic transitions, with most baryonic gas in the universe existing in ionized form at low density. In the hot intracluster medium along the Sloan Great Wall, atoms are stripped of many of their electrons, forming a thin, high-temperature plasma. Collisions between electrons and ions excite remaining bound electrons to higher energy levels, and when these electrons drop back to lower levels, they emit photons in specific spectral lines. Free electrons scattering off ions also emit a continuous spectrum known as Bremsstrahlung radiation. Together, these processes allow the gas to radiate away energy, though only slowly at the low densities typical of cluster halos. The temperature and spectrum of this emission encode the conditions of the plasma-letting observer's infra densities, chemical abundances, and ionization states from far away. A poetic detail sits quietly in the way each photon emerging from this gas carries the precise imprint of the transition that produced it, with its wavelength set by the difference between two atomic energy levels. In the galaxies embedded within the wall, cooler gas phases occupy a different microphysical regime. The atoms of hydrogen, helium, carbon, oxygen, and heavier elements exist in a range of ionization states, depending on local temperature and radiation fields. Electrons hopping between levels in these atoms, and ions, along with molecules rotating and vibrating, produce characteristic emission and absorption lines. These lines mark the presence of specific elements and conditions. Dust grains composed of aggregates of atoms arranged in solids absorb high-energy photons and re-emit them as lower-energy infrared radiation, smoothing the local energy distribution. At this scale, the balance between heating and cooling depends on how frequently particles collide, how easily photons escape, and how strongly radiation fields bathe the gas. A quiet scientific mystery remains in the detailed behaviour of gas at extremely low densities and complex ionization conditions, such as those found in the filaments connecting clusters within the wall. Observations suggest that this intergalactic medium contains diffuse warm to hot plasma, but direct detections of its faint emission remain difficult. Simulations predict that a large fraction of the so-called missing baryons in the local universe resides in this warm, hot phase, yet measuring its exact amount, temperature distribution, and chemical enrichment is challenging. How efficiently this gas cools, how often it condenses into galaxies, and how it responds to feedback from star formation and active galactic nuclei are areas of ongoing research. The Sloan Great Wall, with its extended filaments and clusters, provides a natural setting for such plasma, yet much of it remains only indirectly traced through absorption lines in the spectra of background sources. 3 soft ironies emerge from this microphysical view. The first is that the grand structure of the wall depends on the collective behaviour of particles so small that their individual actions cannot be followed, yet their statistical properties reproduce the same simple laws in every environment. The second is that the visibility of the wall relies on photons produced by discrete atomic transitions, while the majority of its mass remains locked in particles that never emit light on their own. The third is that the cooling of gas, which allows structure to condense into clouds and stars, often proceeds more slowly in the lowest density regions, so that the emptier spaces retain heat longer than the denser ones. Within molecular clouds, microphysics shifts again. The gas is cold and mostly neutral, and collisions occur frequently enough that rotational and vibrational transitions in molecules become important cooling channels. Molecules radiate energy away at specific frequencies, allowing dense regions to shed heat and continue collapsing. Dust grains provide surfaces where atoms can meet and form new molecules, particularly molecular hydrogen, which does not radiate efficiently on its own under cold conditions. Cosmic rays, high-energy particles that permeate the interstellar medium, ionize a small fraction of the gas-producing ions, and free electrons that participate in chemical reactions and couple the gas to magnetic fields. The interplay between these reactions, radiative processes and magnetic forces, determines the temperature ionization fraction and stability of the cloud. A lesser-known detail is that small changes in the abundance of key coolants such as carbon monoxide or singly ionized carbon can shift the balance between heating and cooling, altering the density at which gas becomes thermally unstable. Differences in metallicity between galaxies along the Sloan Great Wall, reflecting their past star formation histories, thus affect microphysical behavior in ways that cascade upward into cloud structure and star formation efficiency. A quiet uncertainty persists in how universal these microphysical relationships are across different cosmic environments. While the basic atomic and molecular processes obey the same laws everywhere, the relative importance of each mechanism depends on density, radiation fields, and composition. Filament galaxies exposed to stronger ultraviolet backgrounds or influenced by nearby active nuclei may host interstellar media, where certain species are more ionized, altering the cooling curves that dictate how gas responds to compression. Determining how much these subtle differences matter for large-scale evolution remains an open question, linking laboratory physics to the structure of the cosmic web. 3 additional soft ironies reside in this inner regime. Only took slight variations in atomic energy levels to produce the rich forest of spectral lines that identify elements across cosmic distances. Yet those variations arise from the same simple quantum rules repeated for every atom of a given species. Only took rare collisions in thin plasma to generate X-ray photons that trace the deepest gravitational wells in the wall, while far more frequent collisions in dense regions produce radiation that is easily trapped and reprocessed. Only took the smallest departures from perfect neutrality in cold clouds to enable magnetic coupling and chemical complexity, guiding the evolution of gas that will eventually form stars. At the smallest considered scales, radiation acts as both messenger and regulator. Photons emitted in hot cluster gas, warm ionized regions, and cold molecular clouds carry away energy, allowing systems to cool and evolve. The same photons once escape travel outward through the filament and into intergalactic space, eventually reaching distant observers. In dense environments, absorption and re-emission transform radiation fields, shaping ionization fronts, heating dust, and driving subtle forces on grains. Radiation pressure, while usually small compared with gravity on large scales, can matter locally near luminous stars or active galactic nuclei, altering gas flows in their immediate surroundings. In every case, the interaction between matter and radiation at the microphysical level sets the terms on which larger structures change slowly over time. At this depth, the Sloan Great Wall can be understood as a continuous field of atoms, ions, electrons, dust grains, and photons arranged in patterns that arise from gravity and expansion, but regulated by microphysical processes. The vast filament, its clusters and galaxies, and the clouds and cores nested within them all depend on the rates at which particles collide, radiate, and react. At the outer edges of the Sloan Great Wall, the density of galaxies declines until the filament's outline softens, and the long chain of clusters and groups gives way to regions where matter becomes sparse. The narrative now reaches the innermost conceptual boundary of the topic by remaining at this interface between structure and near emptiness, describing how the wall merges into its surrounding voids and how the pattern of the cosmic web gives way to stretches of space where almost nothing resides. The path has moved from the broad cosmic web through the wall's spine, its clusters, galaxies, disks, clouds and cores, down to microphysical processes. Here it turns to the transition back outward from structure into silence, where the presence of the wall is defined as much by what lies around it as by what lies within. A scientifically accepted fact frames this region. Cosmic voids occupy most of the volume of the observable universe, even though they contain very little matter compared with filaments and clusters. These voids are not completely empty. They harbour a low density of galaxies, gas and dark matter, but at levels far below those found in structures like the Sloan Great Wall. Around the wall, such voids extend for hundreds of millions of light years, forming broad bubbles into which matter only slowly flows. The boundary between the wall and neighbouring void is not a sharp edge, but a gradual decline in density, as galaxies become more widely separated and small filaments taper off and disappear. In deep surveys, this boundary appears as a transition from continuous structure to isolated points, then to near darkness, where only occasional galaxies remain. A quiet, factual detail lies in the motion of matter near this interface. Galaxies and gas at the edges of the wall experience gravitational pull toward the filament, yet also feel the effects of cosmic expansion that pushes everything apart on large scales. In underdense regions, the expansion dominates, causing voids to grow as matter drains toward surrounding structures. As a result, the Sloan Great Wall can be seen as one of the ridges bordering these growing empty regions. Over billions of years, matter continues to flow along the dark matter spine toward the wall and its clusters, while the void interiors become even more rarefied. The interface between wall and void thus represents a dynamic balance between local attraction and global expansion, recorded in the slow drift of galaxies along and away from the filament. A quiet scientific mystery remains in the detailed connectivity of the web at these low densities. While simulations show that filaments and walls percolate through the cosmic volume in an intricate network, observations at the faintest levels are limited by sensitivity. It is uncertain how many very thin filaments extend from major structures like the Sloan Great Wall into the surrounding voids, or how completely the web fills space at the smallest detectable density contrasts. Some galaxies in apparent isolation may in fact trace extremely low density bridges that current surveys cannot resolve. Whether the wall stands as a relatively isolated feature or as one segment of an even more extended pattern of barely visible threads remains a subject of ongoing study. From the perspective of an observer mapping this region, the transition from structure to near emptiness is gradual but clear. Within the wall, galaxy redshift maps reveal continuous chains and dense knots. Toward its edges, those chains break into smaller groups, then into pairs, then into single galaxies separated by large distances. Beyond that, the map shows broad regions with only a few points of light where estimates of density fall far below the cosmic average. The wall's presence becomes most apparent. When contrasted with these voids, it is a ridge of relative fullness surrounded by vast spaces where the universe's matter budget contributes little to local structure. This contrast emphasizes that large-scale structure is as much a pattern of underdensities as of overdensities, with the wall and its neighbouring voids forming complementary halves of the same arrangement. At this innermost conceptual layer, the Sloan Great Wall becomes less a discrete object and more a defined region within a continuous field of density variations. The cosmic web extends beyond it, but its local environment is characterized by enhanced clustering along its spine and dilution around its borders. The processes described in earlier sections, cluster dynamics, galaxy evolution, gas flows, cloud formation, and core collapse all operate within this context supplied by matter that has collected along the ridge and framed by volumes where such processes are scarce or absent. In this sense, the boundary between wall and void marks the practical limit of where the detailed astrophysical complexity associated with dense environments is concentrated. Beyond that boundary, the voids stretch outward until they meet other filaments and walls that belong to neighbouring sectors of the cosmic web. On even larger scales, the expansion of the universe gradually weakens gravitational connections between distant structures, so that in the far future, only the most strongly bound regions remain mutually visible. For the present epoch, however, the Sloan Great Wall sits as one extensive feature among many linked by gravity to other superstructures, but also separated from them by hundreds of millions of light-years of underdense space. Light from galaxies embedded in the wall, and from those isolated in the voids, travels together toward observers, carrying with it a record of these contrasts in density and structure. Standing at this conceptual inner boundary of the topic, the description has followed matter from its broad distribution in the cosmic web into the specific superstructure of the Sloan Great Wall, down through its internal hierarchy, and out again to the threshold where structure fades into near emptiness. The region now described is neither purely filament nor purely void, but the transition zone where the influence of the wall diminishes, and the quiet of the low-density universe begins to dominate. In that quiet, the wall's role is simply to mark a place where matter has gathered more than average, leaving surrounding regions correspondingly depleted. The universe continues to expand, the web slowly evolves, and the Sloan Great Wall remains one of the many large features that trace the pattern of matter across the observable cosmos. In the deep quiet of space, the Sloan Great Wall rests within the wider cosmic web, its long filaments stretched across distances that light crosses only over immense spans of time. Galaxies along its spine continue their slow motions, orbiting within clusters and drifting gently within halos of dark matter. Their light travels outward in all directions, soft and steady, carrying records of stars, gas and dust that formed under the guidance of gravity and the microphysics of cooling and radiation. Around the wall, broad voids extend in every direction, their low densities shaping the contour of the filament more by absence than by presence. In these underdense regions, a few isolated galaxies move almost alone, while the background expansion gradually increases the distances between all structures. Inside galaxies along the wall, stars burn at measured rates, some nearing the ends of their lives, others newly formed from clouds that have recently cooled and collapsed. Cold gas continues to circulate through disks, clouds shift and fragment, and dense cores complete their quiet collapse into compact objects that begin to shine. Dust grains absorb and re-emit starlight in long wavelengths, smoothing sharp contrasts into a faint diffuse glow. In cluster centers, hot plasma remains suspended in extended halos, slowly radiating X-rays as it balances gravity and thermal motion. On smaller scales, still atoms, ions and molecules follow the same simple rules as they exchange energy, emit photons and respond to local fields. Everywhere along the wall, from the largest stretches of filament down to the smallest regions in dense clouds, motions continue at a pace set by gravity expansion and the cooling of matter. The pattern of the wall holds its shape across cosmic time, while its internal details change gradually, with stars forming aging and ending in cycles that renew gas and alter the composition of the interstellar and intergalactic medium. In the surrounding darkness, light from these processes continues its long journey outward, spreading through the expanding universe with calm persistence, leaving the Sloan Great Wall suspended in a state of extended, unhurried evolution.